Hi, my name is Miranda Rudolph, and I work with Professor Wass of the Aerospace Engineering Department examining 3D textile woven composites. So what are 3D woven composites? Most aerospace applications use composites that are made of unidirectional fiber-reinforced materials laminated together through the use of a matrix material. The most common problem is that in between the fiber toes, where the matrix epoxy is, if the composite is exposed to many stresses, in between the fiber toes, it's only as strong as the matrix material is. Now, in order to address this issue, 3D weaving was introduced. It binds the fibers through the use of a Z fiber, which runs parallel to the warp direction and is drawn from top to bottom up and over the weft fibers. The goal of my summer research was to get a better understanding of the impact of the varying architectures in composite materials. I wanted to obtain Young's modulus as well as Poisson's ratio through experimental tension tests as well as computational tests. The composites that I looked at for the SURE program consisted of carbon fibers, glass fibers, Kevlar fibers, and epoxy arranged in 3 different orientations. Architecture 1. The thin hybrid. The thin hybrid has the top 2 rows carbon fiber toes and the bottom 3 rows are glass fiber toes. In the thin hybrid, as well as the other 2 architectures, the Z fiber is made of Kevlar. Architecture 2. The thick hybrid. As you can see from the image, in the top 2 rows you have carbon fiber toes, and in the bottom 7 rows, in comparison to the 3 of the thin hybrid, you have glass fiber toes. The third architecture I looked at was the CGC thick hybrid, or carbon glass carbon thick hybrid. In this case, the top 2 rows as well as the bottom 2 rows have carbon fiber, and the middle 5 rows are glass fiber toes. Again, the Z fiber is made of Kevlar. Volume fractions of the fiber toes. It's important to understand what the fraction is of actual fibers in comparison to the matrix filler within a toe. In order to address this issue, I was able to take microscope photos that zoomed in on the individual fiber toes and see how much fibers there were in comparison to the epoxy. Now, I use these volume fraction percentages in a CCM model, which is the concentric cylindrical model, which gives me an effective Young's modulus taking into account the fiber modulus as well as the epoxy modulus, so that I can upload isotropic material properties or transversely isotropic material properties into my abacus model. MTS tension test strain contours. These images show you that the strains that occur are dependent upon the architecture. The top image shows you that wherever there's a green is where the Z fiber is weaving in or out. This shows you that the strains are higher and there's a strain concentration area where the Z fiber is weaving in and out. The bottom picture shows that because of Poisson's effect, when you pull in the X direction, or the weft direction in this case, it causes a shrinking in the warp or the Y direction. DIC strain contours. Now, these images were captured by taking many pictures from the MTS tension test and running them through software called Aramis. The DIC can then tell you what the strain fields are. On the left, you see similar patterns among all 3 samples. Although the magnitudes may be different, the same pattern is seen. Again, the same thing on the right side. The same pattern is seen, although the magnitudes are different among the materials. Experimental data. On the left side, you can see that there is a stress-strain curve. Now, from the stress-strain curve in Hooke's law, you can get the Young's modulus. On the right side, you could see the strain plots. Now, from the strain plots, you could get Poisson's ratio. By using Poisson's ratio comparison of negative transverse strain over axial strain, we can get a Poisson's ratio for each of the samples. Now, onto the computational. For our abacus modeling, this just shows that all 3 architectures were examined in abacus. The proper material properties were assigned and ran through the very similar tests. Abacus strain contours. As shown from the experimental contours, you get a certain strain field. Now, the difference with computational analysis is that you're not just given a strain value from DIC software. So I initially put the unit cell in with given dimensions. So I knew A and delta L and L. So as long as I could output the force, the reaction force from a certain displacement, I could get Young's modulus. The same with Poisson's ratio. Once I did both the computational and the experimental analysis, I was able to compare the two. On the left, you could see the stress versus strain curves for the thin hybrid as well as the thick hybrid. Now for the thin hybrid, the errors are relatively high. However, for the thick hybrid, the errors are relatively low. This allowed us to compare the modulus value from both computational and experimental results. On the right side, we were able to compare Poisson's ratio from the strain plots. Now, as you can see, these errors are much higher, but this may be due to the fact of the certain constraints we put when we made the computational model. It allows for lower strains in certain parts, which may lead to higher error. Computational versus experimental in terms of strain. As you can tell from both the left and the right images, the strain contours are very similar. Now, the magnitudes are different, and this may be due to the inaccuracies in the SolidWorks model. However, it is capturing the right patterns. So what might cause the differences? Well, manufacturing issues. The model doesn't take into account any voids or matrix pockets or pre-cracking that typically occurs around the voids. So this may either underestimate or overestimate because it's assuming a perfect architecture. Also, the way the fibers are tied together in the model. They're bound to set right on top of each other, which limits movement among the fiber toes. Also, in Abacus, we only look at one unit cell, whereas if we looked at 4 or maybe 9 unit cells pieced together, we may get more accurate data. Also, when I was making my model, I took an average of all the fiber toes, which doesn't take into account how tight the weaving is or where the fiber is at relative to the Z fiber. So what's next in this test? Well, the model we have does a fair job at predicting what the hybrid panel is doing during the MTS testing. The next step would be to see if we can refine the model in order to decrease the percent errors that we're getting, and especially in the strains and the Poisson's ratios. After the model is refined to a decent percent error, we can look to see when we do shock tube testing, compression testing, and bending testing, if the values that we get from the calculations and formulas that we have compared to what the computational values are. And this will tell us how well our model is doing after those percent errors are decreased. So that's my work on 3D textile woven composites. Thanks for listening.